Hello again for my final video in this multi-series of videos, which are a part of my course requirement for the KIG 2018 thermodynamics course. And in this final video, I will be going through the concept of absolute entropy. Okay, so uh, as we've seen before, when we were talking about enthalpy values, we we wanted to find a common datum for reacting systems because when you had those different property tables like steam tables or ideal gas tables, you had different datums, different arbitrary datums for these different tables. And when we were taking values of delta H for the same table, those datums would cancel out and we would just get the value. However, for reacting systems, since the product is different from the reactant, we need another way of basically calculating delta H, which is where the concept of an enthalpy of formation came about. However, when it comes to entropy, we also set a common datum. But however, instead of thinking of the standard conditions or the standard reference state as we did for enthalpy, instead now we refer to the third law of thermodynamics for our new reference. And the third law is basically a statement about entropy because it says that when you have a perfect crystal, so let's say if I have a perfect crystal like diamond, for instance, that's going on and on in this tetrahedral shape, right? So when you have a perfect crystalline structure like diamond that goes on and on, okay? And when you have it at 0 Kelvin, such that there is no kinetic energy for any of the molecules. So none of these molecules are vibrating. So there are no vibrations. There is no internal energy. When you have these conditions, we can say that the absolute entropy is zero. And this creates the perfect data or common data that we need for our calculations. Okay. So again, in this final part, they said, observe that the steam tables from table A7 through A18 do not provide absolute entropy values because the absolute entropy values are only applicable when they're calculated relative to this 0 Kelvin state for per pure crystalline structure, right? And so we find these absolute entropy values again in our table A25 in the Moran textbook. And so, well, in this part, they're basically talking about how you can use tables 823, 823E, which is the empirical, to find to give the value of the absolute entropy for selected substances versus the temperature at a pressure of 1 atm. So essentially the standard state, right? And so we bring our attention to this particular formula, right? And this is basically the equivalent of what we saw before, where we had HF and delta H, and we basically, oh, well, let me go back to the formula itself. It was this, essentially, this formula right here. And so the entropy equivalent of this, yep. So the entropy equivalent of this formula here is basically this, right? So we find the absolute entropy and we find the difference at P and P reference. And the ln shows up because of the integration over dq by t, right? Which is just entropy. And so we have the difference between the P reference, which is just 1 atmosphere, and whatever the specific state is at some pressure P. And so we can get, well, here they've basically stated it for the ith component of an ideal gas mixture. So if you had a bunch of different gases, okay, you can sort of find the individual entropies, right? Individual absolute entropies. And then for the total mixture, you can just add them up and get the total. And so this here is an example of a basic calculation that we can do. This just so happens to be Y, which is the proportion of oxygen that's being used, the proportion of nitrogen that's being used, and they're relative to one another. And in this case, we're saying that the ideal gas model applies, right? So as you can see, they've gone through with this whole calculation. And because you have this assumption of the ideal gas model, recall that for an ideal gas model, you can just add the values together and get the total.